Imagine a world where humanity no longer wrestles with the weight of energy crises or the burden of environmental harm from fossil fuels. Instead, we turn to the stars, or rather, recreate their power on Earth. This isn't a vision of a distant future. Thanks to China's world-renowned fusion project, the experimental advanced superconducting tokamak, or EAST, we are getting closer than ever to making it a reality. China's artificial sun has broken yet another record, sustaining temperatures of over 70 million degrees Celsius for a staggering 1,056 seconds. This remarkable feat pushes the boundaries of science and brings us a step closer to harnessing limitless, clean energy. Join us as we dive into the revolutionary possibilities of fusion energy, explore the technology behind EAST, and uncover what this breakthrough means for the future of energy on Earth. The artificial sun is an ambitious nickname for EAST, a tokamak-based fusion reactor developed in China. EAST is essentially a large, donut-shaped device that aims to replicate the sun's natural energy-producing processes. It's different from traditional nuclear fission, as it generates energy by fusing hydrogen atoms together instead of splitting them apart, like in typical nuclear power plants. The goal of projects like EAST is to demonstrate that nuclear fusion, just like the reaction taking place in the core of our sun, can be recreated to produce reliable energy here on Earth. What makes fusion particularly appealing is its potential to provide clean energy without producing harmful greenhouse gases or the long-lasting radioactive waste associated with traditional nuclear power. Earlier this year, EAST set an extraordinary world record, running at superheated plasma temperatures exceeding 70 million degrees Celsius for 1,056 seconds, just over 17 minutes. To put this into perspective, that's 5 times hotter than the core of the sun. Understanding this breakthrough requires a grasp of how nuclear fusion, the process underlying EAST, works. In simple terms, fusion occurs when two light atomic nuclei, typically isotopes of hydrogen, collide at extremely high speeds and fuse together. This process releases a vast amount of energy, following a principle connected with Einstein's famous equation, E equals mc squared. For fusion to occur, 3 main conditions must be met. Extremely high temperatures. Fusion requires temperatures of tens of millions of degrees to overcome the natural electrostatic repulsion between positively charged hydrogen nuclei. Magnetic confinement. Since no material can contain plasma at such extreme temperatures, powerful magnetic fields are used to confine the plasma and prevent it from touching the reactor walls. Stability over time. Efficient energy production relies on maintaining stable plasma conditions for long durations. The tremendous achievement of EAST lies in meeting all of these criteria for longer than ever before in the fusion industry. The importance of sustaining plasma at such high temperatures for over 1,000 seconds cannot be overstated. For years, one of the largest hurdles in fusion research has been achieving stable and sustained conditions. With this breakthrough, EAST has demonstrated significant progress towards developing fusion reactors that can operate continuously, paving the way for future large-scale energy generation. This record isn't just about setting a new runtime, it validates the feasibility of extended operations needed for practical fusion power plants. If reactors can continuously produce energy at these levels, fusion may finally transition from experimental technology to a real-world energy solution. The heart of EAST's success lies in its cutting-edge tokamak reactor design. The tokamak concept, initially developed in the Soviet Union, uses powerful magnetic coils to create a toroidal, or donut-shaped, magnetic field that confines the superheated plasma. During the record-breaking experiment, EAST maintained temperatures 5 times hotter than the sun's core, sustaining the plasma within this magnetic cage. This incredible feat was possible, thanks to superconducting magnets. EAST leverages advanced materials in its magnetic systems, capable of withstanding intense conditions while maintaining performance. Precision plasma control. Advanced diagnostics and algorithms help scientists monitor and stabilize plasma behavior in real time, preventing disruptions. Upgraded materials. The reactor's inner wall and components are made of heat-resistant materials designed to endure prolonged exposure to extreme conditions. Each of these advancements marks a critical step toward overcoming the technical challenges of nuclear fusion. While EAST's achievement is groundbreaking, it is important to understand the obstacles that still remain before fusion can revolutionize energy production. Energy input versus output. Currently, fusion reactors consume more energy to create and sustain fusion reactions than the energy they generate. A key milestone is achieving a net positive energy output, meaning the reactor produces more energy than it consumes. EAST's experiments bring us closer to this goal. Material durability. Plasma temperatures can reach millions of degrees, requiring materials that can withstand prolonged exposure to such extremes. Developing robust reactor walls is an ongoing area of research. Economic feasibility: building and operating fusion reactors like EAST and the International ITER project involves significant funding. Reducing costs to make fusion energy commercially viable remains a critical challenge. Scalability: to power entire cities, fusion reactors must be scaled up while maintaining efficiency, safety, and operability. Fusion has the potential to solve some of humanity's most pressing energy and environmental challenges. Clean energy: unlike fossil fuels, fusion doesn't produce harmful greenhouse gas emissions, making it an ideal solution to combat climate change. Infinite fuel supply: fusion relies on isotopes of hydrogen, which are abundant on Earth and in seawater, ensuring a virtually limitless fuel source. No long-lived radioactive waste: unlike nuclear fission, fusion reactions do not generate dangerous, long-lived radioactive byproducts, significantly simplifying waste management. Additionally, fusion energy could provide energy independence, freeing nations from geopolitical tensions surrounding fossil fuel supplies. It offers a long-term, sustainable solution to power global development while protecting the planet's ecosystems. The achievement by EAST is a significant milestone, but it is just one step on the path to making fusion a widespread energy solution. Many global collaborations are advancing the fusion frontier. ITER, the International Thermonuclear Experimental Reactor, currently under construction in France, represents the next major leap. Once operational, ITER aims to achieve net positive energy output. EAST's future goals: EAST will continue to refine its capabilities, with the aim of sustaining plasma for even longer durations under increasingly stable conditions. Commercial deployment: experts predict that commercial fusion reactors may become a reality within the next few decades, provided research and funding continue at their current pace. Fusion energy represents a scientific dream where physics meets engineering. The work being done today will lay the foundation for a cleaner, sustainable future powered by the energy of the stars. Humanity's relentless curiosity and innovation have always driven us to push the boundaries of what is possible. The success of EAST's record-breaking experiment is a testament to that spirit. China's artificial sun has shown us that fusion energy is not just a distant dream but a tangible possibility within our grasp. As we marvel at the potential of harnessing the same energy that powers the sun, it's clear that fusion technology could become the key to addressing the dual crises of climate change and energy scarcity. For science enthusiasts and academic minds alike, this is a thrilling time to join the conversation and contribute to shaping the energy solutions of tomorrow. The era of fusion energy isn't just a promise for the future, it's an unfolding reality. With each new breakthrough, we're inching closer to an age where humanity can finally draw its power from the infinite brilliance of the stars.